Alright guys, so I'll be hosting the computer architecture Midsem prep workshop. I'm Sreenikethan here, and yeah, you're always free to welcome to ask doubts in the chat, or if you need any specific question that you're unable to get past, you can always mention it and we'll try to sort it out. Okay. So I'll be starting with the session now. And yeah. So for the very first chapter, which is introduction, there's a lot of theory stuff. But then the most important concept that I would like you guys to know is the difference between CISC and RISC type of processors. Okay. So starting off with MIPS, this is what you have used a lot in your course, and it's basically an architecture of CPUs. So what an architecture basically means is how a CPU is constructed and what kind of operations it can perform. So MIPS we call this also an instruction set architecture. So we also have other architectures like x86 and then ARM architecture, which you might have heard Apple is using for the past few years. So similarly, MIPS is such a architecture, and what it dictates is what kind of registers it has, what is the structure of the CPU, and what kind of instructions it takes, and all these things. The programming language which we will be using to write the programs for a MIPS type CPU is called MIPS assembly. So the naming, I hope it's clear with you guys. Now there are two terms which you might have heard, which is CISC and RISC, and let's just discuss some quick differences between them. In this, this is the full form: complex instruction set computer, and RISC is a reduced instruction set computer. So the laptops and phones that you have right now, probably, or well, I'll say laptops for the past 20, 30 years, they have been following the CISC architecture, while most of the phones, they have been following RISC architecture. So first of all, why do we need multiple architectures? Why not just come up with one architecture and use it for every single device? There are some practical considerations for this. So let's go in a sequence. The first point is that for CISC type architecture, the code is simpler to write. In the sense, in the assembly language, if you write, let's say, one line of code, it will do certain things, right? Now, similarly, if you want to perform the same action in a RISC type computer, you need to write 4 or 5 lines of code. So as a programmer, writing code is lengthier in RISC type systems, but it's simpler in CISC type systems. Now, the second point is that since the instructions are simpler, all it means is that, the same instruction has a capability to do multiple things. So when you're implementing a CISC computer as a hardware designer, which is, like the one that takes the code from the programmer, right? So as a hardware designer, you will have to work your brain a lot more, and there are a lot more difficulties and complex paths and circuits you need to design to run CISC type code. Whereas on the other hand, since for RISC instructions, the code is really simple, so you can also implement the hardware of it much easier, and it will be more power efficient and overall more efficient in general. The third point, which is the main difference, is that memory access and calculation can be performed in the same instruction for CISC type architectures. So in CISC computers, you might have studied in MPI x86 type assembly. Now this x86 type assembly is a CISC type instruction set. Whereas what we are going to discuss now in CA course is a RISC type language or computer, which is what MIPS does. So in x86, you could remember that one instruction will access the value from memory and also perform an addition operation and then store it in a register, for example. But then in RISC, you have to have separate instructions. So your first instruction will be loading the value from memory. The next instruction will perform the actual addition within registers. The third instruction will store it back to the memory. So your actions are split into multiple steps. Now, when it comes to CISC again, since one instruction does multiple things, it is not magic, right? Like one instruction cannot run in the same time if it does more things than the other instructions. So let's say an addition operation where one version of it will add 2 registers, one version of the addition operation will add a memory value with a register. So both of these variations will take different amounts of time, right? So processors may take multiple cycles to execute the same instruction. Whereas in RISC, all instructions are executed within a single cycle. So by design, it is required that every instruction will complete executing in a single processor cycle. So some of the terms we will explore as and when we go deeper into this workshop. So let me just reiterate. x86, which you learned last semester, the 8086 stuff, that is all under CISC, and RISC, the best example is MIPS. And even the Apple M1 chips and M2 chips, all those chips, they follow a RISC type system. So I hope everyone's clear so far. You can give a thumbs up in the chat. And yeah, if you guys have a doubt, you can just type it in the chat. Okay, so moving on, let's start with the next chapter, which is performance, right? So we have a bunch of calculations in this chapter, but it's really simple and it's really straightforward once you understand the purpose behind such formulas. Most of them are really simple. So let's get started. Now, the very first formula is, or term, let's call it, it's called execution time, and it's measured in seconds or milliseconds or whatever you want to use. So very simply put, it measures or it denotes how long your program takes to run on a given computer. So let's say I have my computer and a video rendering project. Let's say I'm exporting a video from CapCut, right? Now that might take 2 minutes to render on my laptop. But then if I have a 15-year-old laptop, which I have which my parents had given me, that it might take 15 minutes or 20 minutes to render the same video. So execution time is simply how long it takes for the same program to run on different systems. The next term which we are talking about is called performance. So this performance is not a real number in the sense that it doesn't have any units to it. But then it's more or less something that gives you an idea of how fast something is. And you can think of performance as the reciprocal of execution time. So in other words, if a program takes 1 minute on one computer and 10 minutes on the second computer, can we say that the performance of the first computer is larger than the second computer, right? Because since the time taken is less, we can say that the performance is much greater. Now, this comparison of performances between two computers is done with this thing called N, and N denotes the ratio of two performances. So since it's a ratio, there is no unit to it, but then it gives how many times a computer is faster than the other. So if you think about it, if my first computer takes 10 minutes, 1 minute to do a task, and the second computer takes 10 minutes to do a task, I can simply say that, the first computer is 10 times faster than the second computer, right? So that is what this ratio will calculate. Okay. Now, these three formula are pretty much one category of formula. That's the very basics, right? And they're not real formulas, honestly speaking. They're just simple terms, okay? Next concept which we can learn is something called a clock cycle. So this is a term which we had seen earlier, and it simply means it is the smallest action which can be performed by the CPU. So as we discussed earlier, let's say addition is an operation the CPU can perform, and memory access is an operation that CPU can perform. Maybe subtraction, multiplication, each of these things are, one operation, and that's executed in clock cycle. And yeah, there is the unit for this simply called as cycles. Now, the next term we'll come across is something called clock period. And clock period basically tells how long is one clock cycle going to last. And since our CPUs are really fast these days, the duration of one such cycle will be in very small units, picoseconds, nanoseconds, and stuff like that. But it is again a unit of time. And similarly, if you take the reciprocal of the clock period, you get something called clock frequency or clock rate. And the unit is usually in gigahertz, or which basically has a hertz in the unit, because hertz is the inverse of seconds. So the smaller the clock period, the faster your CPU is, and the higher the clock frequency, your CPU is faster. So these two are reciprocal of each other. Now, this is a new term which we don't come across very often in the consumer world. But then since we are studying this course, this is a measurement that is taken quite often. And it is called CPI. And it stands for cycles taken for an instruction, or cycles per instruction or clocks per instruction, both are the same thing. So what this means is that when we take instruction as a concept, there are some instructions that might take 2 cycles, right? So the simple examples which we had discussed earlier, like addition, multiplication, or let's say addition and subtraction, might take only 1 cycle. But certain operations like multiplication and division, they might take multiple cycles on a processor. So for those instructions, there can be multiple cycles. So that's why you should not confuse between a cycle and an instruction. They are related, but they may not always be the same. And how do we know this information? Is by calculating or by observing the CPI value. And yeah, it's a simple calculation only. Just take the number of cycles taken to run something and then divide it by the number of instructions you had given it. So this is it for the formula. This pretty much summarizes all the formula for performance. You can take a screenshot of this if you want and just keep it for reference, or like take a photo of this. And we will be using these formula to solve go through the numericals. All right, so let's continue. There's a very simple question. All right. So let me just see if this pen thinks. Right. Yeah. Anyways. Sorry, just give me a moment. I'm trying to figure this out. Yeah. So we have a very simple question here, which states that there's a computer A that runs a program in 10 seconds. Okay. And there's a computer B that also runs the same program in 15 seconds. So what we have constant in this case is the program. And when we say the program is constant, that means the instructions given to the computers are the same. Okay. So we are having the same code, and we are also assuming the same MIPS architecture is used on both the computers. So with everything being kept same program, same architecture, all this stuff, only we can observe that only the timing is varying, right? So let's note this information down in a proper way. So let's say E1 is the execution time of the first computer. Let's call it 10. And E2 is the execution time of the same program, but in the second computer, or you can also say EA and EB. This is 15. Now we want to calculate how much faster is computer A as compared to computer B. So we are simply calculating the performance ratios, right? So that's simply equal to the value of n, and we can calculate it as P2 divided by P1 or PB divided by PA. Or if we actually substitute the formula, it is 1 by E2 by 1 by E1. I mean, I'll just use 2 and 1 because it's a bit more convenient. And if you simplify this ratio, you're basically getting E1 by E1 by E2. And if you substitute the values, it is basically or yeah, you can technically we are calculating how much faster A is than B, right? So we have to do performance, or wait, just a moment. Yeah, since we are calculating how much faster A is than B, we can substitute performance 1 by performance 2. Is what we are calculating. And in that case, the formulas will turn out to be like this. And what comes out is basically 15 by 10. And that is equal to 1.5. So our result here is basically that A is 1.5 times faster than B. Okay. So I hope this very simple numerical you guys have understood. So let's move on to the next question. So this is a bit more involved question. So let's start solving it, right? What they're saying is there's a compiler designer and they're trying to decide between two code sequences. Okay. And what it means by code sequences is basically stating that there are two programs. Here there are two separate programs, unlike the previous case. Now there is a concept called class of instructions. So what a class of instruction means is that as I said earlier, there are multiple types of instructions, right? Like very basic ones, like addition, subtraction. There's a bit more lengthier ones like multiplication and division, and then there's other stuff like memory access and all these things. So there are different types of instructions, and each type of instruction might take multiple clock cycles to execute. So, and as we discussed, that's where the CPI measure or the CPI value will come into use, right? So they have made it a bit abstract here, and they're just simply calling it class A, class B, and class C type of instructions, right? So what this means is there is for whatever instruction, how many ever instructions occur in class A, each of them will take one clock to execute. And if there are like 10 instructions in class B, there will be 20 clock cycles taken for it. Similarly, for every instruction in class C, there will be 3 clock cycles taken for it. So this is how you'll be given the CPI information, this one way of being given it. Now, for a particular statement, so we are talking about a compiler here, and a compiler is a program that takes the human readable high level code and then converts it to low level assembly language, right? So let's say they are compiling the C language to the MIPS assembly. So the design is considering two separate code sequences that can be generated for the same C statement. So let's say in C, you're doing a statement that creates a for loop or something. So for the same for loop, you probably have two ways of writing it in assembly. And that's what these two code sequences are talking about. So the C level statement is the same, but there are two ways to write it in assembly, right? These are the two sequences they're talking about. So these are the, for the given sequence, these are the like number of instructions that are required in each type of class. So let's take this first sequence, right? So in sequence 1, we have class A, which has 2 instructions in it, and class B instruction, which has 1 instruction in it, and class C instructions, which has 2 instructions in it. So there are a total of 5 instructions that are executed when you run the sequence 1 type of code. Now, similarly, when you run the sequence 2 type of code, there is 4 instructions in class A, 1 executed in B, and 1 executed in C. So there are 6 total instructions executed in sequence 2. Now, you can simply look at, there are 5 instructions in the first one, second, and there are 6 instructions in the second one. But that information alone is not enough to conclude that, just because 5 is smaller than 6, you cannot just say that, sequence 1 is faster. You actually have to calculate the timings or like the durations, or let's say the number of clock cycles for each sequence. So let's start with that. So we are calculating clock cycles, right? Let's calculate clock cycles for sequence 1, all right? So what happens is we have to basically multiply every type of instruction with every class that there is, okay? So basically for A, we have 2 into 1 CPI. For type B, we have 1 into 2 CPI. And for type C, we have again 2 instructions and 3 clocks per instruction. So this is equal to 2 cycles. This is equal to 2 cycles again. And this is equal to 6 cycles. So if you add all of these up, you get basically 10 cycles. So let me just summarize. You have different types of instructions, and each type of instruction takes different number of clock cycles to execute. So if you simply multiply the corresponding values and you add all of the cycles values up, you get 10 cycles for the first instruction. And this 10 cycles basically says that sequence 1 takes 10 cycles to execute. Okay. Now, similarly, if you take for sequence 2, let's do the same calculation. So we are multiplying 4 instructions with 1 clocks per instruction. For class B, we have 1 instruction which takes 2 clocks each. And for the class C, we have one instruction which takes 3 clock cycles. So let's do the calculations. And if you add all of them up, this basically gives you 9 cycles. So if you think about it, even though the first sequence has lesser number of instructions, the second sequence still takes one less clock cycle than the first sequence. So this basically concludes that our answer is that sequence 2 is faster. So I hope everyone understood this numerical, and this basically uses all the formula that we have learned so far. Okay. So if you guys have doubts, you can mention it. Otherwise, you can just acknowledge. Alright guys, let's move on to the next concept. So this is called as Amdahl's law. So this introduces a concept called parallelization. So that's where you are having multiple instructions that run simultaneously. So what we have seen so far is that if there are like 10 instructions, each instruction runs one after the other, correct? So because it's a case in a lot of programs that the output of one instruction is required for the input of the next instruction. So that is called a serial or a sequential operation. So it's like, when you're doing something in real life, let's say you're cleaning the room or something, you have to do everything in a sequence, right? Like first you clean the desk and then you clean the other table and then you clear mop and sweep the floor. So there is a sequence to it. Now, in contrast, parallel programs are basically those programs where the instructions in them do not depend on each other. So if you have multiple CPUs, you can have each instruction to run on a separate CPU. So if you're talking about calculations in mathematics and you're doing 5 separate equations, and all these 5 equations don't have any connection to each other, as in they don't use any variables from the other 4 equations. So you can have 5 CPUs where each CPU does the calculation separately. So parallelization is a really useful concept when you want to speed up your task in wherever it's applicable. But yeah, it is always the case that you can't, or it is not always the case that you can parallelize every single part of your program. And it is very usually the case that some part of your program has to be sequential and the remaining part of the program can be made as parallel. So what does this mean? Let's just draw a quick diagram. Imagine these are all the instructions of your program, okay? And each instruction is executed one after the other. Let's call this as time. So let's say this portion of the program is executed sequentially, okay? And then this portion of the program has parallel code in it, or parallelizable code in it, where it is possible for you to execute this code in a parallel fashion. Now let's say if you have only one CPU, you will execute, if you have only one CPU, you can only do one thing at a time, right? So even though the code is capable of being parallel, you execute it in serial nature. But if you introduce a second processor, let's call this P is equal to 1 because we have one processor. Now, if you have a second processor, maybe this portion, it will still run sequentially, as in you cannot use the benefit of 2 processors, but then the parallel portion will take, exactly half the time. Now, and similarly, if you have, P is equal to 3, you can draw another case where the sequential portion will still remain as it is, but then you'll have 1/3 of the original execution time, because the parallel part can be run 3 times as fast. So this is the basic idea behind parallelization. And now we are going to calculate the performance speed up you get when you have a system that is parallel, able to be run in parallel nature. So let's say you have multi-core CPUs these days, right? So it's kind of relevant in that sense. Now, when it comes to the formula, it's also really straightforward. we have basically this thing called F that denotes what fraction of your program is run in. I think this is supposed to be series. Okay, so this basically denotes what fraction of your program is run in series. Okay, what this means is, it's in this case, if we just take this, let's take it, 0.6. So 60% of my program is able to be executed in series, and the remaining 40% of my program is parallel capable code. So what we are going to do is, this N formula basically calculates the speed up, the performance speed up. This is the same N as what we discussed earlier. So in the formula, this term denotes the time taken by the series part, and this portion denotes the time taken by the parallel part. So as you can see, F is the series portion, right? And 1 minus F basically calculates the remaining portion of the program, which is parallel. And for whatever duration it takes, we are going to divide it by the number of processors, because more the number of processors, the duration will become shorter, right? So this is how the formula works. So let me just, yeah. Yeah, so this is how the formula works basically. You have this portion which denotes the sequential part, and this portion which denotes the parallel part. And when it comes to speed up, your denominator is always going to be smaller than the numerator. So that's why this N value will always be greater than equal to 1. Okay. So this is the Amdahl's law, which basically calculates, how much of a speed up are you getting as and when you add more processors. So let's solve a quick question with this. And we are given a very simple statistic. We are given very simple inputs, where it is stated that 90% of the program can be parallelized. Okay, parallelized, and there are 5 processors which are located in the system. So let's just plug these values into the formula, right? So if you think about it, let's draw a quick diagram for our understanding. Okay, this is parallel and this is sequential. So in our formula, this is what the F value denotes, and this is what 1 minus F value denotes. And we are told that 90% of the program is parallel, and 10% of the program is mandatory to be run in sequential nature. So when we substitute these values in the formula, this is what we get. So F value is 0.1 plus 1 minus F is 0.9 divided by 5. So when you do the calculation, you basically, let's just do it here. So you basically get a 3.5 times speed up of the of the whole system, or in the program in this case. So this gives you a N value of 3.57. So what it means is, when you run the same program with one processor and then you compare it to running the same program with 5 processors, you'll get a 3.5 times speed up. And as you can see, this is not equal to a 5x speed up, because that's what we have learned as per the Amdahl's law. Okay. So similarly, we can also try out another numerical, but it's the same values, but then we are having 1,000 processors in this case. So yeah, it seems like an absurd value. There's no real CPUs, CPUs which are cheap enough to have 1,000 processors. But just for an understanding, let's try to calculate this. So we have 0.1 here as the sequential part, and then 0.9 for the parallel part divided by 1,000, right? So when you think about this term is negligible, because when you divide 0.9 by 1,000, it becomes really small number, that when you add it to 0.1, it still doesn't make much of a difference. So you can kind of approximate it to 1 by 0.1, and this basically gives you a 10x boost. So what you can conclude from this is that even if you have 1,000 processors, you can't really go more than 10 times the speed up boost, right? Because the 10% of the program is still has to be run in sequential nature. So this concludes the performance type numericals. This is the Like there's really simple formulas, and all you have to do is just understand how they work. So I hope you guys are clear with this. You can drop a message in the chat or give a thumbs up. Okay, guys. So let's start with the next chapter, which is the MIPS assembly and all the brief stuff about the MIPS CPU architecture. So we will be like learning like code instructions, assembly instructions in this. Okay. So we have discussed some aspects of this earlier. So let's reiterate. The first point is that instruction set, and this basically is the collection of all the possible actions which are which a CPU can do. So let's say addition, subtraction, multiplication, division. There are some floating point operations later on. So all these things. And instruction set which we are using is the MIPS instruction set, if you want to call it that way. So similarly, x86 has an instruction set and so on. Now, the next concept we need to keep in mind is something called register. So a register is nothing but a 32-bit variable which is located inside the CPU chip itself. And when we say variable, it means you are able to write code which can update its value as well as read the value from it. So 32-bit is 4 bytes, right? So your variable cannot exceed this number of bits, and there are only 32 of such registers. So you can think about it, it's a very limited quantity, right? But the benefit is that it's a really high speed variable, in the sense you can perform actions that are really quick with it. And they're really fast to access and store. So that's why it's useful for the CPU to have registers. All the calculations the CPU performs are done in the registers. Now there are, as we discussed, there are 32 registers, but there are some important ones which you'll be referring to mostly in your code. So the 0 is a register which just gives you the value constant 0. So this kind of seems useless at the moment, but then later on some instructions, they require a register, and in its place if you give a 0 value, this is the best way to do it. Moving on, we have something called temporary registers, and we have something called persistent registers. So there are 10 such temporary registers and 8 of persistent registers. So later when we explore the concept of functions, like functions in C language or Python or whatever, where we can call other piece of code with like arguments and stuff. So that's where these different types of variables will come into play. So apart from that, they both are like same, as in they can store values and you can read from them. The main difference lies in the fact that temporary registers, when you call a function within MIPS, you cannot guarantee that the values in temporary registers will be saved, or they might get discarded. But when it comes to persistent registers, when you call a function from MIPS, those values will be preserved when the function exits. So keeping these registers in mind, this is how the format of an MIPS assembly instruction looks for the most part, or the most common types of instructions. So the first term you see is the operator, which is the action that you want to perform, like addition, subtraction, etc. The very first argument you give to that instruction is the output register, or the location where the output value will be stored. The second input is the second argument is the first input that the operation will receive, and the last argument is the second input that the operation will receive. So this is the general structure of an instruction. So the output is the first argument, and the inputs are the remainder of the two arguments. So let's go through some basic arithmetic instructions. Okay. So we have addition, subtraction, multiplication, and division. Let's briefly discuss what each one of them does. So you have the add instruction, which basically takes two registers as input and then performs the addition for it and stores its output in the output register which you specify. So in this example, we have a register called S1, we have a register called S2. It will take the two integers from it, and after performing the addition, it will be stored onto the T0 register. Similarly, there is an instruction called add I, where the I stands for immediate value. Now, this is a new type of argument that you can give to your instructions. As you can see here, in the previous instruction, it was always a register that takes a value and register where the output is stored, right? But in this case, the last argument can be a number which you are typing it in the instruction itself. So this 1, 2, 3 is not stored in any memory or any register, but rather you're putting this 1 to 3 in the code itself. So what this does is it takes the 1 to 3 value and then it adds it to the value in the register. And then the result is stored into the T0 register. Now similarly, there's another instruction called add U. So you might have learned about 2's complement numbers in like the previous courses, and 2's complement notation is used for representing negative numbers mainly, right? But then if you don't want to use the 2's complement logic, and if you want to just add numbers, in the exact form that they are, you can use the add U instruction, which will basically take the two values from the registers, but then it will not perform any 2's complement on it. It will just add the two numbers and store the unsigned version of it in the destination register. So this concept is called as unsigned addition, where you basically do not look at the plus minus sign at the start. And if you, and if you just look at this one, there is an instruction called add IU, which basically takes a register and it takes an immediate value as well, but then it performs unsigned addition to these two values, and then it stores it in the destination register. So these are the four instructions that mainly you'll be dealing with when it comes to addition. Now similarly, there's a subtract operation where it takes the first value, subtracts it to the second one, stores a certain T0. There is also a sub unsigned where it takes these two numbers as unsigned integers and performs the subtraction. Now you might ask, why is there not a subtract immediate like sub I instruction? Because you can simply use the same instruction as add I, but then you can just give a negative number in the third argument. So let me repeat, the sub I instruction doesn't exist because you can use add I instruction and just give a negative number here. Similarly, sub UI also doesn't, or sub IU also doesn't exist. Now, when it comes to multiplication, there are two variations here, right? Because there is a important aspect when it comes to multiplication. That is, when you multiply two numbers, the number of bits of the result can exceed, more than the number of bits that you started with. So if you have like an 8-bit number and you multiply with another 8-bit number, your output can come to 16 bits of size. So the number of bits is literally doubling, right? And you cannot store a 16-bit number in an 8-bit register. So in this case, all MIPS registers are 32-bit. So what happens is when you have two inputs, which are both 32-bit, the output of the value of the operation is a 64-bit number. But then all the 64 bits will not be stored. What they will do is they'll take the rightmost 32 bits and then it will store them in this T0 register. So it's like ignoring the upper 32 bits, and that's what's happening here. But then for the cases where you actually want to use the upper 32 bits as well, you have a second instruction called mult. So these are very similar, just remember that there is an extra T here. So what happens is it multiplies the two values, but then there are two special registers which you can access with a special command. And what happens is the values from the multiplication are split into two halves, the upper half and the lower half. So the leftmost 32 bits and the rightmost 32 bits. So these values are stored into the high register and stored in the lower register correspondingly. Okay. So division also has a similar logic to it. Remember that all of these are integer operations. There is no floating point involved. So when it comes to division, you have the first one divided by the second one, and the remainder is stored in the high register and the quotient is stored in the low register. So you can keep a reference of this when you're learning. Okay. So with this, we can move on to the next type of instructions. All right. So let's try out a sample MIPS program, right? And we are given this, we want to basically perform this kind of a calculation, but then we have to write the MIPS code for it. So if you think about it, we are given 4 inputs, right, on this right side. So we don't have a single instruction that takes 4 inputs and gives an output. So we might have to use an extra register called T0, where we'll be storing the output of some temporary steps, and then we'll be finally putting the result back into S0. So let me just show you. So the first thing we can do is, if you notice, there are two arguments right at the start. Like we can take two of the arguments and then add it first. So let's pick S1 and S2. What I'm going to do is I'm going to take the value of S1 and S2 and then I'm going to store it in the value of T0. So the first instruction that we'll be writing to carry out this operation is to say add and followed by T0, S1, S2. So we are taking the value of S1, which is 10, taking the value of S2, which is 20, and the sum we are storing it in T0, which is equal to 30, right? So this is the very first operation. Now the next operation which we can do is take the output of this addition and then add the value stored in S3 register. So what we're doing is we're taking the big expression and breaking into the smallest operations which we can do. So the next operation is basically take the value of S3 and add it to the existing value of T0 and then store the result back into T0 again. So as you can see, what we're doing is the instruction says add T0, T0, S3. So this also is a very straightforward operation where we are taking 30 as the T0 value. The S3 value is also 30 here. So the sum of this operation will be 60. Now this 60 is again stored into the T0 register. So we can cancel this out and write 60 here. And the next operation which we can do is take the outcome of these three terms and then do the subtract operation with the S4 register. So what we are going to do is basically subtract S4 from T0 and then store the value into T0 again. So as you can see, the instruction format is as follows. We have the output written first. This is our first input and this is our second input. So T0 minus S4 will basically give you 60 minus 40, right? Because that's the value of S4 here. And you'll get an answer of 20. So this value is taken and it is stored into into T0. Now finally, we wanted the answer to be located in S0, right? So what I can do is I need to copy the value of T0 into the register S0, right? And for that, we can use the addition operation. But then what we will do is simply add the 0 value to the T0 value. Because if you remember, the addition operation, it has to take two inputs, right? It doesn't take one input. So if you want to just simply copy a number from one register to the other, we can simply add 0 to the first number. So what happens is this 20 value is then stored into S0. So these are the 4 lines of instructions which you can write that will perform which will execute this statement. So I hope everyone's clear with this example and how to write the code or derive the code for it. Alright guys, so let's again solve a very quick example. And this again involves converting the C level type code into MIPS format. So you will be given these kind of questions in the exam. And what we're doing here is we have a lengthy expression which has brackets, right? So there is operator precedence and all that stuff. So all this sounds complicated, but then it's kind of straightforward if you just think about how you will solve it on a piece of paper, right? So what we have to do is we have to add G and H here. Then we have to find out I plus J, and then we have to subtract the two values. So let me just write it down here. Add G plus H, add I plus J. Let's call this as, X. Let's call this as Y. And then calculate X minus Y. Let's say store it into Z. And then we are going to say F is equal to Z. So this is how the rough order of operations will occur, correct? Or you can also just skip this step and directly store the value into F. So we have 3 instructions that we are going to do, right? So let's start writing them in assembly or MIPS assembly. We are given some assumptions here, which variables to use. So F is S0, G is S1, so and so till J is S4. So our very first instruction, is to add the G and H values and then store it into a temporary register. So I have added G and H, which is S1 and S2, and I have stored it into T0, okay, which is a temporary register. Similarly, I can also take the values of, S3 and S4, which is I and J, and then add them and store its values into T1 register. And finally, we have the values of the two brackets, which is, this is T0, this is T1, and all we have to do is subtract it and then store the result into F. And F here is denoted by S0. So if you look at the third instruction, it's basically subtract T0 with T1 and store it into S0. So this line of code in C can simply be converted to these three assembly lines. And yeah, that's pretty much it when it comes to these kind of questions. So all you have to do is to figure out what is the order of operations that you need to perform. So stuff like, brackets and multiplication and all this stuff, if it's there, you have to, think about the order and plan your steps in that form. Alright guys, so let's move on to the next concept. So far we have discussed all the operations with just registers, correct? So there is another thing called memory, and these are two different concepts. You should never mix up register with memory, and these two terms are not interchangeable. So let's go through what are the differences first of all. So registers, as we had discussed earlier, it is part of the CPU chip itself, right? And it's like, physically comes with the CPU. You cannot increase like the number of registers a CPU has. On the other hand, memory is the RAM stick that you install on your desktop or your laptop. And yeah, it's basically that. You can like buy RAM sticks. And the second point here is that the number of registers is also very less. Is that in this case, we have only 32 registers. But then when it comes to memory, you have a large number of locations available to address in the memory. So it can be measured in megabytes or gigabytes. Now, the third thing is called the least addressable unit or the smallest addressable unit. And this is basically a fancy word that tells what is the smallest value that you can, least number of bits you can store in such a location. So for registers, the smallest value is 32 bits and the largest value also happens to be 32 bits. So anytime you do any operation with the register, you always have to deal with 32-bit data. But on the other hand, for when it comes to memory or your RAM chips, the smallest value is 8 bits, or in other words, it's just 1 byte. So your memory capacity can be a multiple of 1 byte, or you can address 1 byte locations in the RAM. Now, registers have a benefit. They're really fast, but they're also really expensive. That is the reason they're very less in quantity. The memory, on the other hand, it's compared to registers, it's much slower, but it is still quite fast enough that, it fits the purpose. When it comes to registers, each register has its own name, like a dedicated number to it. But then when it comes to memory, you can think of memory as like an array in C language, where you just create an int array of like some 100,000 elements. And that basically is how your memory acts. It is a linear list or linear array, which has a very large number of locations, and you can access any location at any point of time, or you are allowed to store any value at any location for the most part. And yeah, the thing with any type of processor, it's not just CISC or RISC. Any processor can perform operations only on registers, and it cannot perform any calculations on memory values. The memory values have to be first copied to a register, and then the actions have to be performed. Okay. So moving on, we are going to discuss the instructions for memory access, right? Because so far, if your values are in register, we need to put the values in register to begin with, right? So let's discuss those instructions. There are two terms here. One is called load, one is called store. Loading is the act of copying something from the memory to the registers, and storing is the value of like, getting the output from the register and then putting it back to some location in the memory. So with that, we have two types of instructions, loading and storing, right? The first one, it is called LB or LH or LW, where B stands for byte, which is 8 bits, or H stands for half word, where it is 16 bits, or W stands for word, which is 32 bits. So what happens is we are telling the CPU to look at this address in the memory and then load so many number of bits of data into the register. So now earlier we just discussed how everything is 32 bits, but then how come there are multiple sizes here? So what happens is when you load an 8-bit value, it will take the 8 bits from the memory, but then it will store only the last 8 bits of the T0 register and update it. So the remaining 24 bits are not, they are not considered when this operation is run. So similarly, when you run an LH command, it will take the 16-bit of data from the RAM and it will update only the lower 16 bits of the T0 register. Similarly, LW is not an issue. You can just copy all the 32 bits to the register. If you take the opposite of the load operation, it is store. So what happens is it takes the value from the register and it will store the data at the given address. And similarly, there are two other operations which are not exactly related to storing and loading, but we need to know them anyways. So LI is load immediate, which basically is the same logic as earlier. And if you notice, all these commands have only two arguments to it. LI command will take the immediate value that you have provided in the instruction and then store it in the register. So LI is a very simple operation that you can use to copy, just create a variable and create a register and just store some value in it. And similarly, LA is a command that takes the address of a memory location, but then it stores the address itself in the T0 register. So note that the first and the third instructions are different. The first one copies the value. The third one copies the address itself or the index itself to the register. So with this in mind, let's quickly explore a sample C code. We are declaring an int variable x and we are just storing x is equal to 20. So now for the same C code, these are the corresponding MIPS instructions. If you notice, the x variable is supposed to be declared in the memory and it is not declared in the registers. So what happens is, if you write it like this, where x colon with dot word space the value, this is the assembly notation for creating a variable in the memory space. So let me repeat. This is the notation in MIPS if you want to create a variable in the memory, but not the register. So we have to create the name of the variable first, and after a colon, we have to write dot followed by the type of the variable. So since we are using 32-bit variable, we are going to use word. So let's just write dot word here and followed by the starting value that you want to allocate. Now what we are going to do is the next instruction copies the value 20 from the immediate value into the register T0. So this is a completely register based operation and nothing to do with memory, right? So just stores the value 20 in the register. Third is the store word operation. So that is this one. What store word does is it takes the value of the T0 register and then it copies it to the X memory location. So you can notice that the store command, the destination is the second argument. So this is one pattern that you need to keep in mind, where all the other commands have the destination as the first argument, but for a store command, the register always comes first. So the T0 value is copied and stored into the X memory location. So now we also let's explore the array notation, which we have seen in C code, and this basically relates to the offset concept, right? So let me just create an array here with so this is an array of integers, right? So the indices are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, so on, so, right? And I have a value here that's going to be copied. We are going to take the array index 8 and then we're going to add some value to it and then we're going to store the output in the G variable. So this is a C statement code, right? So we are also given some assumptions where let's take G and H, both of them to be as registers. but then the A is an array that is located in the memory. If you remember, arrays are always in the memory because you cannot have continuous register values in the CPU. So the base address of the A variable is stored in S3. Now, what does a base address mean? That basically tells the memory address of the location or the memory address of the array which is located in the memory, right? So if this is my array and I want to know the exact location of the very first element, right? That's what the base address will give me. So what I need to do instead is I need to access the index 8 element from the array. So that means I have to take the base address and then I have to add 8 to it, correct? Because the index location is here. This is what I want to get. But then if you remember, we are also talking about an integer array, correct? So if you have an integer array, each element is equal to 32 bits. So what happens is we have the index number 8, but then each element in the array is 32-bit long or equal to 4 bytes long. So let's keep this in mind, and we need to calculate the final offset, right? So this is the MIPS notation to write the same like piece of code. Basically, we are taking the base address of the array and then we are adding 8 index locations to it. But if you convert it to bytes, it comes out as 4 bytes for each index. So we have to basically do 8 into 4 is equal to 32 bytes. So this 32 is what we are going to write in the instruction. So if you think about it, S3 stores the base address of the array as it is given here, right? Now we are going to add 32 to the base address and we are going to load the word that is located at this position into the T0 register, right? So let me just reiterate. We are going to take the base address of the S3 register, of the array which is stored in the S3 register. We are going to add 32 bytes to it and then we'll store its output in the T0 register. So that's using the load word command, right? And this is the notation. You have to basically write the offset followed by the brackets, and within the brackets you have to write the base address. And now that we have the value of the memory in a register, we can just simply use it in the next instruction to perform like an add operation, where S2 is the H value, T0 is the array value, and then we are going to store that value in S1, which is the G variable. So I hope this clarifies how we can use memory offsets. So you guys can give a thumbs up if you got it, or if you have any doubts, you can please ask in the chat. Okay, so now let's compare the same example, but then we are also storing the output to a memory location with a certain offset to it. So what remains the same? First of all, we are accessing the same location, and second, we are adding the same number to it, right? The only difference between the previous and the current one is that we are storing the value to a memory address and not to a register. So we have to add an extra instruction, as you can see here. So the very first instruction is to load the byte or load the word from the given offset from the base address, right? So if this is your base address, the A value is a base address, we are loading the number which is located at this index. And we are going to store it in the T0 register. The next step we are going to do is add the T0 register with the S2 value, which is the H value here. Okay. And we're going to store it again in the T0 register because let's just override the T0 register since we are not using for any other calculation. Now the third instruction is the interesting one here. We have to store the value at the 12th index, right? So index equal to 12, but then each element is equal to 4 bytes. So therefore the offset is simply equal to the product of these two numbers equal to 48. So the offset that we need to use when you want to refer to the 12th index, the index 12 is basically 12 times 4, which is 48. That is why if you can see here, the notation is also the same, but all we are doing is take the S3 register, multiply with, add 48 to it. So this is an addition operation. The CPU will perform the addition for you in this case. So we're taking the memory location itself and we are increasing the memory location by 40. We are not adding to the value of S3. So if you notice, when we write 32 here, we are not adding 32 to this, right? 32 is not being added to this. We are in fact adding 32 to the location itself. So when we get the value of T0 from the previous step, let's store it in the output register. So that's how the store word operation also works. So I hope you guys are clear with this so far. And there is just one more point and then we'll take a short break. So now you might have seen the instruction so far, right? Which is the add space, like 3 arguments. Now we can, we have to eventually write this in binary format. So this is the instruction format for R type of instruction. So these are called R format instructions. And here we have basically a set number of bits which are dedicated to various paths. So let's quickly go through them. The OP is 6 bits, which basically is the operation code. So for add, there is a special number. As you can see here, like there are 6 zeros that you need to give, which corresponds to the add operation. The RS is the register number of the first register. So if you remember, there are 32 registers, right? And each register has a numeric number associated with it, not just S1, S2, T0, T1. So when you take the number for that, the value for S1 register is 17. So you have to write the number 17 in binary format as follows. Similarly, for RT is the second source register. And similarly, when you have the S2 register, you write it as 18. And RD is the register number of the destination. Now the shift amount, we can ignore this for now because this operation doesn't perform any shift. And there is another thing called function code, which is extends opcode. So for addition, when it comes to addition operation, let's take this example. Okay, so we are adding S1 and S2 and storing the output into T0. So operation here and the function extension function code, if you consider, you basically have to write 0 here and you have to write 32 here. That is the definition for performing the add operation. Okay. Now the next part in this is the source register, which is S1. We have to write it as 17. And for S2, it is the second source and we have to write it as 18. And finally, the destination register is T0 and it is given as number 8. So this is a table which you can check your notes. And these are the numbers that we need to get from it. Shift amount, will leave it as 0 for now. So you have to basically organize your instruction in these 5 to 6 boxes and take these many number of bits which are required for it. So when you do all this and you finally get a number, it will be 32 bits long. And this 32 bit, if you write it in hexadecimal format, you'll get a much simpler way of writing it. So what happens is, this is the machine code. This is the binary code that your CPU will be receiving in order to execute this kind of an instruction. So I hope this is clear. Similarly, there is also something called I format instruction, because if you notice in the previous one, there is no space to include an immediate number, correct? So instead of that, we can we have another format called the I format instruction. So whenever you give a number in the instruction itself, let it be okay, I think this example is wrong. You can ignore it, but okay, just a second. So when you have a I format instruction, you basically have the first 6 bits dedicated to the opcode. The second one is the source register, and the second one is either it is the destination or the source register number. So this depends on the exact instruction that you're using, right? And what happens here is the remaining 16 bits that you can see remaining here, you can use it for the constant or the address that you want to actually encode. So let's say, I'll just pull up an example real quick. Okay, so let's take the example of okay, so let's take, hold on. Let's take the example of the load word operation, and we'll say $T naught, comma 32 with a dollar of S3. So what happens here is that the immediate value in this case becomes 32 in this case, right? So we are going to take the value which is located at the S3 address and take the 32 offset of it and then load it into the T0 register. So if you write in like spread it into boxes, basically the first first 6 bits is the opcode. For the load word operation, the opcode is 100011, and the second part is the source register, which in this case happens to be well, the S3 register. So the binary form for it is one, and but yeah, if it's written in 5 bits. So this is the binary format of the S3 register. And finally, if you see, you also have to write the destination register number, so which is for T0. That is 01000. Now, in these 16 bits, you can write the binary representation of the 32 number. So it's basically a bunch of zeros followed by. So this is the binary format on how to write the like I type instruction format. So I hope it is also clear to you guys. Okay, so we'll take a short 5 minute break and then we'll resume the session after that. Right? Hi guys. So let's continue with the workshop. Right. So let's also discuss another type of instruction. These are called as logical instructions. So there is a concept called bitwise operations, where you take you perform operations that are dealing with each and every bit of the number individually. So you might have heard of the AND operation, AND or XOR. So all these kinds of operations are called bitwise operations. Okay. So for performing bitwise operations, we also have some number of instructions. So there is something called SLL, which is for shifting left. There is SLR, which for shifting, SRL. So these are called shift operations, and these also come under the bitwise category. So all these operations also have an instruction format to it. So you can see it's the same operation. I mean, it's the same format as the R type instruction, but let's just plug in the values for this. So we'll take an example of the instruction. Let's say SLL $T0 $T1 and 2. Okay. So as you can notice, there is an immediate value here because when you're performing a shifting operation, the processor accepts an immediate value for the shift amount. So let's try to encode it here. So the opcode for shift operation will be 0. Okay. The next next part which we have is RS, and here there is only okay, so here the RS value is 0. Similarly, the RT value is the source register, which is this one. So that for T1, the value is 0, 0, 1, 0, 0, 1. And for the destination register is given as. So this is RT and this is RD. So we are taking the T1 as the source register, we are taking the T0 as the destination register, and we are having a shift amount of 2, right? So 2 in binary is 1, 0. So when we have these parameters, this is where we are basically using the shifting operation. And when you notice the function here is given as 0, 0, 0, 0, 0, 0. So there are 6 zeros here. So this is a way which it is technically R-type instruction, but then for bitwise operators, you can express it in this format, where especially when it comes to shifting, you can give a value in this case. So now let's also discuss conditional operators. So that's when we have branching, right? So in conditional operators, we are talking about branching mainly. So let me just show you an example. Yeah. So here we have two types of instructions. One is called branch if equal and branch if not equal. And there is also a non-conditional branch operation called as jump. So there are total of, these are the three types you will usually come across. So branch if equal basically tells that if the RS and the RT registers are equal in value, then the code will start executing from a given label. Now again, what is a label here? In this case, if you see, this is the assembly generated code, right? So we'll go in depth for this later, but what you can see is that for certain instructions, you can give a label here. And a label basically tells that this is, like a name given to a specific line of instruction. And similarly, we can also give labels to like other lines of instruction. You can have multiple labels in your assembly program. So what happens is when you give this kind of an equation, you're basically telling it that when these two registers are equal at that point of time, we should jump to the label that is given here. There's another instruction called BNE when it says branch not equal, which is the opposite of this one. So that happens when you have two registers, but then if the values are compared and they are not equal, then it will jump to this label. There is a third type of instruction called J, which basically says that regardless of any condition, it will always skip the line in front of it and just directly jump to the label. So now let's look at this statement which we have in C. Okay, so we're having a simple if statement and we are going to write it in assembly. So we are the way how conditionals work in assembly, MIPS assembly, is that you need to think of the converse case. So you need to always think of executing the else part first, and then you should try to execute the you should check the condition for the else part first, and then you can check the condition for the actual decide part. So 3 and 4 are the ing values, right? These two. So we are going to basically compare S3 and S4. Now, when S3 and S4 are equal, then we are basically going to jump to the L1 part of the code, which is this, right? But then if imagine I and J values are not equal. So when the values are not equal, this branch statement will not run, correct? As in it will evaluate, but it will not jump to the label. So what happens when the branch is not equal? It will run the next line of code, which is the subtract statement. So this is what I meant earlier when you have to write the else part of your code first and then followed by the normal part of your code. So let's look at it. So when the branch is not equal, it will perform the subtract operation like G minus H and store it into S naught, which is the F value, which is good. Now imagine the branch was equal, right? When in the case that the branch was equal or like the condition was equal, we can directly jump to the L1 label. So that is this line of code. So what happens in L1 label is it adds the S1 and S2 registers, which is G and H, and it stores it into the output, which is S0, which is the F register. So if you notice how when the condition is equal, we jump to this line of code. But when the condition is not equal, we run this line of code. Now, if you think about it, imagine this jump statement was not here. So when you check this condition, let's say it was not equal and the branch does not happen, then this subtraction runs, correct? But then if you notice, the very next line of code is the addition again. So what happens is both the statements are getting executed at the one after the other. So that is not a decide behavior. So what we have to do is we have to keep an unconditional jump here. As in, when the code reaches this line of code, what happens after that is that it should jump to a point which is not interacting with the L1 branch. Okay, so in this way, we ensure that only one of the statements run at a given time. So I hope that's clarifying things about the conditional operators. So similarly, we have loop statements as well, which are basically basically variations of the conditionals. So let's look at loops here. So consider this line of code here for in C language. So we are basically checking whenever this condition is true, where save is like some like a register, it's an array. Okay, so this is an array, and we are basically checking if the value at this index is equal to a register k. So what we are going to do is you can just look at this line of code where basically we are getting the value of k, which is S5, and we are checking if it is equal to the value of T1. And here T1, we are assuming it as the value of the the array location. So what happens is we are basically getting the base address of the array in the T1 register, and then we are we are taking the base address, we are getting its value, and then we are storing it in the T1 register. Now in this line of code, when we can ignore this, just see this one. When you compare the value of sy with t1, we are checking if the branch is not equal, as we discussed earlier. So when the branch is not equal, we are going to jump to the L2 section of code. Now in this case, what happens is we are having, this is the loop, right? But we are going to create a label L2 that occurs after the loop. So in this case, we can basically see that we are adding, like if the branch is not equal, then it will, jump to the L2 branch. But then here we are checking for the loop whether condition is equal. So when this is the case, we will still execute this line of code. So we are basically taking the S3 register, we are adding 1 to it, and then we are storing it back into S3. And then we are again jumping to the location L3, which basically takes you back to the start of the loop. Okay, so similarly, when this keeps looping, this is your entire body of loop. And when the loop terminates, it will finally go to the L2 section, which is the part where the loop ends. So now let's discuss the concept of procedures. Okay. Okay. So for procedure calling, the idea is basically that you have, like, let's just compare with C code or something, right? Or like C programming or Python, where you have a function that's defined somewhere in the code, and you want to keep reusing that function because repeating the code is not a good practice, right? So there are benefits of creating functions, which, you can take arguments, you can do some processing, and it will return a value. So when it comes to MIPS assembly, this procedure calling is the concept where we tell the computer to, give the so and so inputs to the function, execute it, and then give the return value back. So there are 6 steps when it comes to executing a function. So first of all, function accepts inputs, right? So there are 2 values. There's the A0 and the A1 registers, which are the 2 registers where the function will take as an input. Okay. So the first operation is done by the calling the main function itself. So wherever you are writing your code, you should store your required values in the A0, A1, A2 or A3 register. You're given 4 arguments. And the next step you need to do is transfer the control to the procedure. So now that you've stored the arguments in place, then you can just start the function, let the function start running. Now within the function, or within the procedure, you can have to acquire storage for the procedures. So if you remember, there are S0 all the way till S7, right? Now, what if your main code had 8 variables like this, but then your function, let me just write this. Let's say your function also needs all the 8 variables to be used. So if this is the case, your function cannot overwrite the values that were used by the main function. So what it does is it stores the copy of these values in the stack. So there is a concept called stack, which is a special portion of memory, which is just used for storing temporary stuff like this, and then they're removed immediately after the purpose is done. So yeah, so this third step basically tells, or is basically the actions where we take a backup of the existing values of S0 to S7 and then store the current values which we want in these places. The fourth step is the actual procedure of the actual code of the procedure. So there's not much to explain in it. And the fifth step here is you have to place the result in the registers. So now when a function runs, it usually returns a result, right? So for that, we have V0 and V1. So in these registers, your function can store the return value in it. And what happens is finally the procedure will end the code and then it will return to the place which started the function, right? So in this case, it will go back to the main code. So, and in this case, you also have to basically run some commands which will put the original values of S0 to S7 back to the registers. So there are two instructions when it comes to jump and when it comes to calling procedures. So one is called jump and link, which you can see here, which basically stores the return address of the main code, and then it sets the current instruction position to that of the procedure. So in short, what it does is it stores the current location in a special variable, and then it hands over the control to the function. Now, why did we store the current address in the variable? Because when the function completes, it should know where to go back to, right? So that's where we have the special register called RA. And PC is the program counter, which is the same as what you learned in MPI. And program counter stores the address of the current instruction. Now there's a second instruction called jump return, jump and return to the address, which basically takes the value of RA that got stored earlier and it updates it into the PC register. And it behaves like the return statement. Now there is a concept called leaf procedure and non-leaf procedure. The idea is that leaf procedures are functions that do not call any other functions. If you notice in this, this is a C code, right? But if you notice in this, there is no other function being called in this. There are variables declared, some calculations are being done, and then you're finally returning the value. But in case of non-leaf procedures, let me just show an example. So in the case of non-leaf procedure, it is when the function has another function call inside it. It could be the same function itself, that doesn't matter. So this is a factorial function where you can see that it is again calling another function. So when it comes to a leaf procedure, you don't have to be very strict with the variables. But then when it comes to non-leaf procedure, you have to explicitly write code that will back up the current variables and then prepare it for the next function call. So with this, we can start the multiplication concept, which mainly will be covering the Booth's multiplication algorithm. Okay. Let me just. So let me just give a quick overview on what multiplication is, in terms of when it comes to writing code for performing the multiplication. So when we do pen and paper multiplication, right, that's really simple, as you might have seen. So yeah. So let's say we are doing 13 into 23 or something. So when we write it, we write one row at a time, right? So the first one is 39, followed by we are writing 13 twos are 26. And when we write it like this, we can add the corresponding columns. So this is the answer that we get when we multiply two such numbers. Now we need to do the same thing for binary as well. So we can have 1 0 0 1 0 or So when we multiply these two numbers, let's just we have to do it for every single row, right? So every single column. So when we have 1001, we multiply with 0, we get all zeros. For the second row, we get 1001 again. Again, we get 1001, and then finally we have all zeros. And when you add these up with binary addition logic, this is the answer that you get. But then if you notice, the more that number of bits are there, there are more rows of multiplications or additions to perform, right? So there are 4 operations here, and then there are 7 addition operations that we have just performed here. So these number of additions quickly add up if you're using 32-bit. So in order to reduce the number of actions it takes to perform this multiplication, there's a thing called the Booth's multiplication algorithm. So let's also explore that. So here we have a concept where we are basically going to write the two numbers in a table. Okay, and I will show you the example real quick. So let's just take, I'll write an example first, and then we'll explain theory as and when we solve it. So let's take this as in two numbers which we want to multiply. All right. So we have this number here, which is 0011, and this is the 0100, which is the second number. So let's also get the result ourselves so that we have something to validate against. So when you perform this calculation, it's pretty straightforward, right? And we have a carry of 0, so let's also write it. So this is our 8-bit answer for the 4-bit numbers that we had given as the input, right? So it's basically multiplying 3 times 4, which is 12, right? Now we need to write the Booth, we need to calculate this with the Booth's algorithm, and this is how it goes. So basically we have to write the two numbers, we have to take one of the numbers as Q, take the other number as, A or M or whatever you want to take, and we need to create two columns like this. So this is called the accumulator column, and this is called the, let's call it Q for now, okay? So in the Q column, let's just write the second number which we had obtained, so 0100, that is here. Now you have to add a third column called Q minus 1, and we will explain the purpose of this as and when we do it, okay? So this has 4 bits, right? And this also has 4 bits because we are dealing with 4-bit numbers, right? And this is exactly 1 bit. Now this Q, we can write it as Q0, Q1, Q2, Q3. So, okay. So this is Q3, this is Q2, this is Q1, and this is Q0. And finally, we have Q minus 1 over here. So what happens is when we write the first line, always give the accumulator value as 0. And for the first row, write the Q value as it is. And write a 0 in this place. So now what happens is we need to check at this value and compare it with the Q minus 1 value. So this is the main core of Booth's multiplication algorithm. And when you do that, you can finally look at a table. So this is a table that you have to by heart, which basically tells for what combinations of Q0 and Q1, what is the actions that you have to do. So in this case, what we have to do is that all the bits that are here have to be shifted right by 1 bit. Okay. So that's all that we are doing. So as you can notice here, these are the 9 bits that we are talking about, right? We have to shift right by 1 bit, and what we get here is this value. So we have an extra 0 in this place, and you can see that the 1 has gotten to this place. Okay. Now again, you can compare the two values which are here, and you can again see that there is the same operation being performed as in the Q0 and Q1 values are 0 and 0. So in that case, again, you can right shift by 1 amount, add an extra 0 here, and you can see that the 1 has moved to this location, right? So now what happens is that the next value, as you can see here, is 1 and 0. So when you look at the table, you have to perform this kind of an operation. You have to say A is equal to A minus the M value which you had taken. So you have to perform the subtraction in binary. So what happens is the A value is all zeros. The M value is 0011, which is 3. So basically you have to do the 2's complement logic and do the subtraction of like this 0000 minus 3. Okay. And minus 3, if you write it in 2's complement, it is basically, one second. So yeah, if you have 0011, you have to calculate the 2's complement for this. So first you have to do 1's complement. So it will become 1100, and then you add 1 to it. So 1101. So this is equal to plus 3, this is equal to minus 3. And why did we calculate the 2's complement? It is because we are performing a subtraction operation, right? If you notice here, we have to subtract the A and the M values. So you are doing basically M is equal to 3 as we started in the question, but then we have to write minus 3. So you can calculate the 2's complement for it. And finally, you just have to add the A value with the minus M value. So A is 0. You have to take the minus M value as 1101. Then when you add it, of course, you get 1101 as the answer. Or I think, yeah. So when you do that, you can notice that the A value here has been updated to 1101. The Q value remains the same from before, and that's fine. But then you should also perform a right shift of 1 bit. So as you can notice, the 1101 has come to the next bit in all the places. But then in the start, you have to introduce the extra bit, right? So far in the past, we have introduced only 0. But then you have to basically duplicate what is the digit on the leftmost bit. So this preserves the sign of your answer. So since there was a 1 in the start here, we will also introduce a 1 here, as I have marked in this. So, and again, the 1 will carry over from this end, it will carry over to the 1 in the Q minus 1 column. Again, you can check the two values in the table. When it's 0 and 1, we have to add the values of A and M, right? So the value of A here is 1110. The value of M is 0011. And when you perform the addition, you are going to get the value as 0001. So let me just show it to you. 1110 plus 01. This will cause an overflow. Right? You're getting a 5-bit answer, but our entire question is in 4 bits. So you just have to take the lower 4 bit. Okay. And you can basically store that value here. And yeah, you basically have to just follow the table for this Booth's multiplication. So you can just by heart this. And as you can see, like you have to shift right everything by 1 bit. And this is the answer that you get. And basically after you have performed 4 operations, right? If you notice, this is a starting one. So you can't count this. So there's 1, 2, 3, and 4. So for a 4-bit input number, you have performed only 4 operations. But when you compare it to the earlier example, you had performed 7 operations, right? Because there are 4 multiplications here and there is 3 additions, or like, you're adding multiple numbers. So it becomes like 7 to 8 operations. So you can see that the final answer that you will have is basically the combination of A and Q, right? So you have to combine this A, take this Q here. So 0000 1100. So this is your 8-bit answer to the two 4-bit multiplications that you have done. So it is basically equal to 12. And as we had checked earlier, the answer which we are expecting is also 12, right? Which is, yeah. So as we had discussed earlier, the answer for this operation is supposed to be 12, and we have gotten the correct answer. So this is how Booth's multiplication works. So I'll just quickly summarize it. You basically have the columns A and Q, where A is set to 0 and Q is set to the Q value that you have in the question. And you have to create a column called Q minus 1. Okay. Then look at the last 2 bits, which is here Q0 and Q minus 1. Then follow the table, what action we have. So when you perform that action and finally you have to shift right by 1 bit, you can repeat the whole process one more time and just keep doing it for 4 times because we're using a 4-bit number. And remember, at the left side, we have to introduce we have to duplicate the existing bit. So if there's 1 here, we have to create a 1 here. Okay. So once that is done, you will get an answer like this 12. And that basically concludes your Booth multiplication process. So I will also quickly go through like how to implement the MIPS code for this. So, when we, we're not going to do this, of course, we're not doing Booth's multiplication ourselves, but then we need to write the code in order to perform the multiplication. So let's just say we have, let's say mult rs, rt. So this is the operation that stores the results in high and low. So this is the 32-bit register, right? And this is also a 32-bit register. So when we multiply two 32-bit numbers, you can see that the output will be a 64-bit number. So as you know, every register is only 32 bits. So we are going to store the high product, the operation will store the result in a high special register and another special register called low. Now these two registers you cannot access directly. So there's a special command which you can, or special instruction which you can use to access the values. So this is what we're going to do, MFHI. So this basically says move from the high register into, let's say, $T0. So what this does is, so let me just take an actual example in this case. So we have two registers, S0 and S1. So we're going to multiply these two registers and then the output is stored in high and low. So in this case, we have to run this special instruction which says MFHI. So it takes the value of HI and then it stores it in the register that you have given. So in this case, T0 will contain the upper 32 bits of the multiplication. So similarly, MFLO is a command that takes the name of a register, let's call it T1, and it takes the low part of the result and then it stores it in the T1 register. So these are the two commands which are really simple that you can use for getting the 64-bit result of a multiplication operation. So yeah, these are the three instructions in MIPS which you can use for getting the full product. So all right, guys. So I guess let's wrap up the session by now. And if you guys have any doubts, you can please mention it in the chat and we can discuss it. All right, guys. Thanks for attending today's session. So, wishing you all the best for your midsems. And Sarthak, no, as far as you know, there is only one CA session, and that is this one. Okay. But if you feel like you need another, you can always mention it in the feedback form, and we'll do our best to we'll see if we can fit another session. And I think you should be getting the feedback form links after the session, just like with other workshops.